Hi. Okay, so what we're going to do now is talk about some of the mathematics that you'll need, specifically taking derivatives and getting us into the exact differential, or what I call the total differential. Okay, so a derivative, that doesn't work very well. So a derivative is a change in something. You typically think of this as a slope. So if you have some curve of some sort, and here's your f of x value, and here's your x value, and so then as x, this is known as the independent variable. This is the dependent variable because f depends on x. And so as you change x in some way, there is your change in x. And then here is your change in f of x. And if you look at the ratio of those two changes, then you will see the derivative essentially. And so you've got a small difference here, so that's a small derivative. You have a large difference here, so that's a big derivative. And so you're basically monitoring the shapes. So the way that we do this mathematically, and you know this when you're like running or walking on a hill, you know, there's like the steep curve and you're like, oh, this is a horrible incline. Big derivative, flat surface, no derivative whatsoever. So where the curve would go like this, there is a point to where f of x doesn't change as you change x. And so these points right here are called saddle points, and you would use those to say, okay, well, the derivative of f of x here, that is 0, and you can use that as an additional equation to the system of equations you would use in solving whatever problem. Always keep in mind, when the slope is constant, derivative equals 0. Put that in the back pocket so you have that to use to solve some of these thermodynamic problems. Okay, derivatives. So if f of x, by the way, this should just be review. If it's not, definitely come and talk to me and we will work it through it. So the derivative, let's pick one. 2x squared, that's a fun function. So the derivative written like this, so the change in f of x per change in x, we use this d to represent an infinitesimal change, is going to be, the way we do this is we take the 2, we multiply it down in front, so it becomes 2 times 2x raised to the 2 minus 1 power. I'm writing all of this out so you can, again, for the refreshing the memory, this becomes 4x to the 1, or we can simply write it just as 4x. And so what this would mean is that the rate of change of the function itself is going to be about 4x. If you have, let's go ahead and draw this out. Whoop, looks something like this. So the rate of this change at any 2 points along is 4x. And so as x gets bigger, then so as x gets much bigger, notice how the slope gets bigger. Well, if x gets bigger, let's just try some. So df of 1 dx is equal to 4. df of 4 dx is equal to 16. So 1, 2, 3, 4. So if this is, say, when x equals 4, and this is x equals 1. So it's changing at a rate of 4 times, and then it's changing at a rate of 16 times. So it's going to get a faster incline, the larger the x value. Cool, so I want you to really start visualizing these functions when you're taking some of these derivatives. Okay, next, I want to talk about chain rule. So f of x is equal to, let's say, 6x times x squared plus 1. Oops, x squared plus 1. Okay, so what you're going to do is substitution, where you, well, not really a substitution, but just to represent this as u and v. And I said chain rule, I'm sorry, I meant product rule. So the product rules is when you're multiplying two together, you have so the derivative of v dx times u plus the derivative of u dx times v. All right, so what we would do then is we would say, okay, so we're going to take the derivative of v first, and that just becomes 2x, multiply that by u, 6x plus the derivative of u with respect to x, which is just 6, multiply that by the v, quantity x squared plus 1. Cool? Awesome. Okay. Next bit would be the chain rule. And I'm going quickly because the power of the pause button, so you can pause and rewatch. So the chain rule, let's say f of x is equal to 3 e to the 4, actually, sorry, 3 x e to the minus x squared. Okay, so the chain rule would then be, so we're going to take the derivative of, actually this is multi-step. So the derivative, we're going to do product rule and chain rule together. So the derivative would be, so we've got du dx, so that's 3 times e to the minus x squared, plus the derivative of v, so that gives us 3x, so that's times our u, e to the minus x squared. Then we multiply by the derivative of the exponent. So this is a chain rule associated with taking the derivative of an exponential. This becomes minus 2x. Cool. And so then let's do another one. Cosine 3x. So the derivative is a much better example of the chain rule. So this is f of x. Then, sorry, pet peeve of mine is when you don't write out what the full part of the equation is. So I was getting mad about that. Okay, so f of x is equal to cosine 3x. So df of x dx is equal to the derivative of cosine is a minus sine 3x. But then we need to take the derivative of what's inside, and this is known again as the chain rule, and that would just be 3. Cool. Hope that's all review. If not, please come talk to me. Math is a language, and if you haven't spoken it in a long time, you're going to be a bit rusty. I fully encourage you to come chat, and we will do a bunch of these examples. Okay, now on to the total differential, or the exact differential, which involves partial derivatives. Okay, so if you have a function that is dependent on both x and y, you have, think about it like bringing in, this is what I call function box. I love function box. Okay, so this is a dial. It's like an analog box, and it has a little needle that'll move back and forth. Well, this is my f of x. Okay, and so now I've got each of these dials. This is my x dial, and this is my y dial. Oops. Actually, make this bigger. F of x, y. Okay, so let's assume that I turn my x knob a little, just a teeny tiny amount, and then the dial goes, it moves a lot. That tells you that x greatly, a small change in x greatly affects f of x, or f of x, y. If I say then do a small change in y and this doesn't move at all, that tells me that I've got a small change in y doesn't move f of x, y at all, then this doesn't really affect f of x, y as much as x does. Okay, so if I want to now, well, how much does x change f of x, y without even changing y? I just want to know x by itself. Well, this is where partial derivatives come in. And so we would represent df of x dx as the exact differential of f of x. But if we have f of x, y, I just want to know how does just x by itself change, and this is what's known as the partial derivative, and it's represented by this little d without a curly d without a tail. And so the way that we would do this is we basically, just like this picture, we treat y constant. So if f of x, y equals 2x squared y to the cubed, say, then the partial derivative with respect to x, we're now going to treat y cubed like a constant. So it's essentially like a number. So the way that we take the derivative of a number, in this case, so we would say, okay, so the 2 is a number, it stays put. Y cubed is a number, it stays put. Now I'm going to take the derivative of just this x squared, which is 2x. Okay, then I can simplify, which is always good to do. This becomes 4x xy cubed. So that's the partial derivative of f of x with respect to x. Now if I want to do the same thing, partial derivative of f of xy with respect to y, well now, likewise, I treat x as a constant, because back to my function box, it would be like I'm just turning the y knob and I'm seeing how the function changes by keeping x a constant. So I'm treating it mathematically just like a constant, and then this becomes, what is this? So 2x squared, that's my constant out in front, multiplied by 3y squared. Let's simplify because it's always important to do that. 6x squared y squared. Cool? Okay. So now what I'm going to do is I want to say, well, what is the total differential then, or the full or exact differential of how f of x, y changes when I change both x and y? And so what I would do then, and I'm going to keep this here because we're going to use these. I'm going to say, okay, I want to know what is df xy. So this is the total differential. And I'm going to write it over here so we have more space. df xy, whoops. And I will note right here, you will use this a lot. When you're stuck in a problem and you're like, how on earth does the Gibbs free energy change with respect to pressure and volume? I'm not sure. You have an equation in your back pocket because you can write out the total differential without knowing anything about the system. Go team. We'll practice this in class. Okay. So I'm going to say this out loud carefully and get a cup of coffee first. I'm going to say this out loud carefully, and I'm going to repeat the same phrasing so you kind of understand the theory behind this differential and the way you should be thinking about it. Okay, the total differential or exact differential of the function f of x and y, dependent on two variables, is equal to the partial derivative of f with respect to x. How much does the function f of xy change when I change x, multiplied by the actual change in x. So that would be how much does the dial move when I turn this knob, multiplied by the actual amount that I've turned the knob. That's this. Plus, same thing. How much does f of xy change when I change the y knob, multiplied by the actual amount that I've changed the y knob, the exact differential of how much this is actually changed. Okay? So, how much does the function f of xy change is equal to how much does the function change when I just change x with respect to the amount of x that is changed, plus how much does f change with respect to y multiplied by the actual amount of y that has changed. Okay, so I will now input what we have done. So this equals, so the total differential is equal to, well, this df of x, or partial f partial x, is equal to 4xy cubed, plus, now at this point, partial f partial y is equal to 6x squared y squared. Cool? This might not look like much, but now we have a function based on how much the function f of xy changes with respect to each of the variables. Cool? Okay, I will now show you a really cool trick you can do when it comes to, actually I'm going to pause. Okay, internal energy is a function of both temperature and volume. That's all I have. I know that U changes with both temperature and volume, but I don't know why. So let's explore it. So what I can do is I can write out the total the exact differential, and that's equal to, so here's my function box, and so here's the dial of the internal energy. Here's my T knob, here's my V knob, and I'm going to change temperature, and I'm going to see how much the knob or the dial changes, and then I'm going to change volume and see how much the dial changes. or the needle changes. And so what I know then is that without knowing what this function actually is, I can say, well, partial u partial t multiplied by the actual change in t, then I add the partial u partial v by the actual change in the volume. Cool? So we will use this time and time again, and I can keep going. Let's say my function is f of star, smiley face, cat. Cool? Okay, so then I'm going to say, well, then how many things am I going to have added together? 1, 2, 3. So that means that my total derivative of f is equal to the partial f, partial star, d star plus partial f, partial smiley face, d smiley face plus partial, partial f, my function, partial cat, d cat. Okay? And so if you have 6 things here, you will have 6 things added together. And if you think about what function box would look like for, say, this example, there's my dial, or there's my needle, I've got star, I've got smiley face, and I've got cat. So each of those dials, I would turn each one individually, and then I would see how the needle changes. And if you think about why this is important for thermodynamics, what things can we actually measure in the lab? Pressure, volume, temperature, number of moles, and potential, but we don't do potential really. So really those 4 things. So we're going to have a function. And so what we really have is pressure as a function of volume, N and T. Cool? And you can take the partial derivative of that. We also have thermodynamic potentials. U as a function of T and V. Cool? Incredibly important stuff. Go team, we're going to do an example of this in class. Hope you watched this video before class. If you haven't, well, then go team, we're going to work through it. All right.